Hi everyone. So where we left off, we had been talking about our angular momentum and the components of our angular momentum of our electron in the hydrogen atom. So when we're constructing the eigenfunctions for this solution, we're going to find that our eigenfunctions are the spherical harmonics for our z component of our angular momentum and for our angular momentum squared. What that means is that the spherical harmonics are going to be orthogonal because they are eigenfunctions of Hermitian operators. So let's get into calculating the eigenfunctions. So as we calculate the eigenfunctions, one of the first things we're going to want to do is rewrite all of our equations into spherical coordinates. So when we move to spherical, we want to go back and remember that we wrote angular momentum, or our angular momentum operator, as an h bar over I, and then a position vector crossed with our del operator. So we want to go back to that del operator and write what it should be in spherical. So the del operator in spherical is r hat, and then the partial derivative with respect to r. In the phi hat direction, we're going to do 1 over r and the partial derivative, or sorry, that's the theta, partial derivative with respect to theta. And then in the phi hat direction, 1 over r sine theta. And you can actually do the exercise to move from Cartesian to spherical and find this out, or you can find this information probably on the inside cover of your book. So that's how we get to our del operator in spherical. Then the next thing we want to do is get to our position vector in spherical, which is easy enough. It's just the magnitude of r in the r hat direction. And so that gets us to our angular momentum operator being h bar over I. And then we want to do each of these operations. So our r crossed with r hat, and then dr, right? R crossed with theta hat, and then d theta, and then r crossed with phi hat, and of course this r is all the way through, crossed with phi hat, and then 1 over r. Oh, that's where I'm missing stuff. I should have a 1 over r here as well. There we go. So this r cancels out with that 1 over r and this 1 over r. Sine theta, d theta. All right, get all that stuff in there. So this r out front here only survives with this first one, but this first one, r crossed with itself, is going to give us 0. This second one, the 1 over r and the r out front here are going to cancel, and r crossed with theta hat is going to give phi hat. And then this one, again, this 1 over r and this r out front are going to cancel, and r hat crossed with phi hat is going to give us a negative theta hat. Okay, so once we do all that, we can simplify our angular momentum operator to h bar over I. The first term does not survive. The second term is just phi hat and then a partial derivative with respect to theta. And the third term will point in the negative theta hat direction, and we've got 1 over sine theta. And this should be, mess this up, this should be a d phi up there. Partial derivative with respect to phi. And that is our momentum operator in our spherical coordinates. And then we want to talk about our unit vectors for these things. So as we're moving to spherical, we could write our unit vectors theta hat as cosine theta, cosine phi, I hat, and cosine theta, cosine, or sorry, that should be sine. Back it up. Sine phi in the j hat direction. And then negative sine theta in the k hat direction. And that is just from taking our Cartesian coordinates, right, and giving ourselves kind of a dummy location and figuring out the relationship here between r theta phi and x, y, and z. So that's our theta hat direction. Our phi hat direction can be had by simply taking negative sine phi in the I hat direction and cosine phi in the j hat direction. So if we want to put that into our momentum operator, we've got something that looks like this. So negative sine phi I plus cosine phi j hat so lots of trigonometric functions. Gonna have to go on 2 lines here. And hopefully not mess up any of my thetas or phis. But always double check me, right? Okay, so that very big long statement where I've just replaced my theta hat or my negative theta hat and my, well, really just my theta hat because I left the negative sign, and my phi hat there. So when you take that a step further, so we've got things like 1 over sine and cosine here, that'll give us a cotangent. So we can take that just 1 step further in simplification. And we'll go 1 step further and say that, for instance, our x component of our angular momentum looks like negative sine phi. So here's where we're picking out all the things that have an I hat. So negative sine phi I hat, partial derivative of theta. And then in my second term, the I hat happens to be a cosine theta, cosine phi, and we're going to take that times the 1 over sine theta. So that's going to give us a cotangent theta cosine phi, right? And then partial derivative with respect to phi. Similarly, we can write our y component by just grabbing all those y component items. So h bar, I, cosine phi, d d theta, sine phi, cotangent theta, d d phi, and then our z component. Now our z component, remember that's what we're gonna try to find our eigenfunctions for, our z component and our L squared component, our angular momentum squared. So the other thing that we need to find is our ladder operators. So that's why I found Lx and Ly. So our ladder operators that we're going to want to have in spherical. Remember, we defined our ladder operator. Our raising operator is going to be the Lx component plus I Ly, and the lowering component is going to be the Lx component minus I Ly. So we're going to substitute in Lx and Ly that we've just figured out here. Right? So what do I have? I have raising or lowering, either way. We'll just stack these equations on top of each other. I've got negative sine phi plus or minus I cosine theta. So we're grouping things together, like instructions, d theta, minus cosine phi plus or minus I sine phi, both times, there's a multiplier here, so both times cotangent theta d phi. And since we can say that this, the cosine theta plus cosine phi plus I sine phi, or minus I sine phi, is going to give us an exponential, so just use Euler's identity of plus I phi or minus I phi, depending on whether you've got the plus or minus in your equation. We're going to substitute that in, and we're going to have for our ladder operators a plus or a minus h bar e to the plus or minus I phi. And of course, this comes out in both of these, right? So then you have d theta plus or minus I cotangent theta. So that's where this I in the front went, got distributed through. So I cotangent theta d phi there. Right, so that is our ladder operator. We can take that a step further. So if we take this definition, and I'll go on to another page here. If we take that definition and we say, okay, what happens when we use a raising and then a lowering operator? We just end up having a negative h bar squared, an instruction to take this derivative twice, a plus cotangent theta, so that got rid of the one of the i's, d theta, then a plus cotangent squared theta, an instruction to do this derivative twice, and then a plus I d phi. And that is and double check me using that equation on the previous page, that if we apply the raising and then the lowering operator, these are the instructions that we're following. Now, remember that we could write our angular momentum, let's back that up. We could write our angular momentum operator in terms of the x, y, and the z component, but because the raising and lowering operators are in terms of the x and y component, we could write our angular momentum in terms of our raising and lowering operators and also our z component in this way. Right? So because of that, we can now write, by combining all the things we've just figured out, our angular momentum operator squared, right, is going to be instructions to take derivatives in this way. So remember, when you do this, you're going to go from right to left. You're going to take the derivative with respect to theta, then multiply by sine theta, then take the derivative, right? So we're going to do our instructions in this way. And then our next component. Right, so that is our angular momentum squared that we're going to put in our back pocket as we figure out our eigenfunctions. So now that we have that angular momentum squared in spherical, right, that's the important thing here. We're trying to see if this looks like the spherical harmonics. We can determine our eigenfunctions. So remember, this is where we were trying to get to. We're trying to determine our eigenfunctions as a function of theta and phi. That's our eigenfunction. And it should be an eigenfunction of both our angular momentum squared and the z component of our angular momentum. But when we're taking it as an eigenfunction of our angular momentum squared, it should have an eigenvalue that is equal to h bar squared L plus 1. So let's write out that eigenequation. So that eigenequation should look like this angular momentum squared operator acting on our eigenfunction is going to give us our eigenvalue multiplied by our eigenfunction. Right. And so if we, instead of writing this, write what I have boxed in red above, we're going to have an equation that looks like this. It's going to look like minus h bar squared, and this is where I'm just taking the stuff out of that red box and writing it for L squared. Okay, so that's one side of the equation. So that is L squared acting on our eigenfunction. And that should be equal to our eigenvalue multiplied by our eigenfunction. So it turns out that this thing up here, that is our L squared operator, happens to just be the angular equation from the beginning of this chapter. So we've got the angular equation, right, from the beginning of the chapter. So we use that in the beginning of the chapter. Now we've got this F, L, and M instead of that Y. So if you look back to your notes where you have that separation of variables of the hydrogen atom at the beginning of the chapter, this is the instructions, the differential equation that we had at the beginning of the chapter with a little bit of rearranging. So that tells us that the angular equation is also a function, or it doesn't exactly tell us, but our work before tells us that the angular equation, because we figured out that the eigenfunctions of L squared were going to be the eigenfunctions of LZ. If this is the angular equation here for L squared, the angular equation is also an eigenfunction of our Z component. And if it's also an eigenfunction of our LZ. Remember, our eigenvalues of LZ varied. So our eigenvalue for this should be m times h bar. So if we write that eigenequation, this is our LZ component, right? It was just h bar over I, d phi in spherical. That acting on our eigenequation should give us an eigenvalue of h bar times m, or m times h bar, doesn't matter which order, multiplied by our eigenequation. Now this, if we compare it to some work we've already done, this is equivalent to an equation that we already have, or azimuthal, where we had this function phi that was a function of lowercase phi. And we used an m as our value there. So we've already solved that, and we've already normalized it in terms of our spherical harmonics. So the spherical harmonics are the eigenfunctions of these two things. So we got as far as basically creating equations that look identical to something we've already solved, and saying, all right, we've already been here, so our eigenfunctions are going to be the spherical harmonics, which we've already solved for and normalized for our momentum, our angular momentum squared, and our z component of the angular momentum. So solving the Schrodinger by separation of variables created simultaneous eigenfunctions for 3 commuting operators. So let's write that down. Solving the Schrodinger by separation of variables I'm going to be a little bit lazy with my abbreviation. Has led us to, or created simultaneous eigenfunctions So we've got simultaneous eigenfunctions for, what do we have? Our Hamiltonian, for our angular momentum squared, and for the z component of our angular momentum. And these 3 are 3 things that commute. So that does make sense that these 3 operators that commute would lead us to simultaneous eigenfunctions. So we can write this out as our Hamiltonian and our allowed energies, our angular momentum squared, and the associated values with that involve our quantum number L. And remember, our quantum number N is embedded in those allowed energies. So L squared and our quantum number L, and the Z component and our quantum number M. Write the correct. Right, and here our eigenfunctions are the Schrodinger equation, at least the spatial component of our Schrodinger wave function, sorry. So our Schrodinger equation, we can write in a different way. And I'm going to write it with 1/2m r squared negative h bar squared ddr r squared ddr plus L squared times V times our potential times, or plus our potential times V and our energies. Our algebraic solution lets us know that L and M can be half integers. So this is a new way we can write the Schrodinger equation in terms of our momentum operator and in spherical coordinates. So that's a good place to pause this lecture. We're going to pick up next time with talking about the spin.